Good afternoon, everybody. Thank you very much for being here. Thank you very much for being here, and thanks to the organizer for putting together this event. So I kind of misunderstood the organization of the talk, so the sequence of the talk. So I thought that today it was an introductory lecture for high school students. But since there are a lot of people from humanities, I think it's okay. So tomorrow I'll be talking to a supposed audience composed of scientists, and I will talk about how AI is going to impact science. And on Friday I will talk about the physics of AI. So that will be technical. There'll be a lot of concepts of theoretical physics used in understanding AI. Today it's more about which are the basic principles, working principles of AI, open problems, perspective, and these kind of issues. So first of all, one thing that comes to my mind is to ask a question. The question is the following. So you often hear the argument, you often hear the sentence, AI reads a lot of text, has read all the text on the web, and so on and so forth. That's the source of information. But what does it mean that AI reads a book? Do you have an idea of what it means, except for people working in, exactly in algorithms? But what does it mean that AI reads a book? Nothing. I mean, a sentence like this doesn't mean much because, what is it? A program that goes through character recognition, and then what does it do with that? Now, let me start by answering this question. So, reading a book, it's an incredible effort for an AI, and it would be very hard for us to behave in the same manner. So what AI does when reading a book is the following. It takes a sentence, and then there is a program that deletes a word from the sentence. It actually deletes all words from the sentence, one after the other. And the AI has to learn to guess what it has been deleted. So it's imagine you read a book like that, in this way. So you read the sentence, and then just right after you are asked to, a hole is created in the sentence, and you have to remember what was deleted. You have to kind of guess what has been deleted. So when AI reads a book, it means that for all the sentences in the book, it learns to fill the gaps that are artificially generated by a computer program. So when we say that AI, say GPT-3, the old AI that came out 3 years ago, was trained on the equivalent of 100 million books, each one of 300 pages, it means that for all this book, for all the sentences, for all the words, it has gone through this process. It has learned to guess in all possible manners what has been deleted in the sentences. So, and by doing this, not only it learns grammar, but it learns something about the models, because it learns to guess based on context. This, in a nutshell, is the learning process of modern AI. And if you imagine to do that, you immediately realize that it is very complicated. And this is where the power of modern language processes comes from. Okay? And I think this is, we'll get back to this, and this is the key reason why there's been a revolution in the last 4 years. It's because by going through this process, you don't need human intervention. Because the program that deletes words is automatic, it's done by some other code, and the algorithms, the AI algorithms, learn to guess without human intervention. So it's totally automatic, and what this means is that in this way it has been possible to process all the written text in the world all of a sudden without any human supervision, which would be hopeless, right? By the way, a man typically reads much less than 1,000 books in his life. This system learned to guess all these kind of things in a number of books, which is in the order of hundreds of millions. Okay, so just to give an idea. So Okay, so let me start just by mentioning that last year we had a couple of Nobel Prizes that were given for AI, and this is a signal that AI is, entering in our tools for science. And so one prize was given to physics and the other to chemistry. I will briefly describe them, but let me anticipate that I expect life science, new materials, new drugs to be generated by AI tools in the next year. So we will see other Nobel Prizes of this sort given for AI applied to science, and maybe also in humanities, and not too far horizon. So what were these Nobel Prizes about? Well, one was about the so-called Hopfield model, and this is a model in which was described, it was published in the 82, and it's a model in which essentially by observing that synapses in the brain are plastic, so they are modified as learning takes place, then what Hopfield did, I will be very brief right now, what Hopfield did was to show that in fact you can construct a physical system that describes the process of associative memories, so the recalling of a memory as a physical dynamical process in a very complex energy landscape. So essentially what Hopfield did is to put together physics, I mean, in the sense of the dynamics of a complicated physical system with properties of the brain. So it was kind of the first to really show that this was both mathematically and practically the case. And the second one, which I think is more relevant, was given to Geoffrey Hinton, who has a degree in psychology. So it's a kind of embarrassing to give a Nobel Prize to a person that has a degree in psychology, but who created around the same time a generalization of the Hopfield model, in which essentially what he did is he split the population of neurons in two parts. One which more or less is trained like in the Hopfield model, which is visible, accessible, that is subject to external stimuli and so on, and the other which is composed of hidden neurons that are not accessible, kind of hidden variables in the system. And what he showed that by training this kind of system, it's possible to generate new information. So by sampling the configuration of the hidden neuron, the visible one generates new information that is consistent with what it has been learned. So this was, in the 80s, the first example of generative AI. At that time, the performance are very bad, nothing comparable with modern AI, but still this was the first model, if you're interested to go through it, of generative AI, and it's called Boltzmann machine. Then there was another Nobel Prize, and I will talk about it tomorrow, in chemistry. And this is really, so the first two Nobel Prizes had a kind of an historical significance. I mean, these were basic model introduced 40 years ago, etc. But the Nobel Prize in chemistry was given for a code that was written 4 years ago. So it's a totally different matter. I will talk about it tomorrow. And it's kind of impressive what this code does. And so just to put in perspective things, the Nobel Prizes in physics were given for something that was done between the 1980s and 1990s. So it was a kind of a good period for computational neuroscience and neural networks and so on. But since after that, there was what was called the winter of AI. Nothing happened, essentially, except some background research going on in different labs. But somehow the performance of the system were not good enough. And so everything didn't develop much. And then something happens around 2005, and I will show you what happened, that gave a big boost to the research, and then there was a big revolution in 2012. And since then, the field exploded. Okay, and also you can see this because if you look at the energy consumption by computer and cloud center and so on, it changed completely in 2012. Since then, the amount of energy that we are consuming for AI applications and cloud computing and so on has been, this is a log scale, so it's been growing exponentially. And I mean, if we continue at this rate, in 2040, we are going to essentially exploit the energy of the planet. So something has to happen. Either we create new energy or, I mean, at the moment it's just, say, 3 or 4%, but the rate of increase is very high. Okay, so let me just mention 3 things that happened in the last years, and which are probably the reason why you're here today. So big discoveries that have really surprised us and are causing a lot of worries, excitement, and competition. And maybe we'll have the occasion in the round table to talk about these issues, because I think they're very important. So I want to mention 3 things that happened. One is language models that work learning by guessing missing words, as I mentioned to you before. We will describe the working principle more in depth. And these have impressed us. The researcher who actually built the first devices did not expect the kind of performance that we are observing. So we are in a situation in which models are beyond theory. Okay, so theory is running and trying to catch up with performance. Okay, that's the situation. Then there are some incredible systems that generate images. These are called diffusion models. Again, they are based on kind of physical equations, which are run in reverse, and the idea is that they, starting from some noise, sampling some noise, it's possible to generate incredible images that are totally new, though consistent with some learned probability distribution. And then another big discovery was the protein folding algorithm that I will describe tomorrow, that is going to change a lot in chemistry. Now, let's just describe what are these systems in terms of their size, just to start with. So at the beginning, the neural network, at the beginning, the first performing models of neural network date back at 2010, 2012, and their size was a few million of connections. So I will describe in details, but you have neurons that are connected by weights, and the number of these weights was order a few million. Now, since then, the growth has been enormous, and now GPT-4, the one that you actually use when you ask questions to ChatGPT, ChatGPT has a size of 10 to the 12 trillions. Okay, so imagine you have a system, software system that has 10 to the 12 parameters that have to be tuned. It's something that was totally inconceivable a few years ago, and it's kind of hard to understand how to control this system. We know how to train it, but then understand what it does, it's another matter. So first thing is these are enormous systems. And for those of you who know a little bit of, say, Bayesian theory or statistics or whatever, you know, Occam razor. You know, Occam razor tells you use as few parameters as possible to make predictions. Simplicity should be the driver, you know. Whereas these systems are actually working in the opposite regime. They have an enormous number of parameters, exactly the opposite of Occam razor. Okay, and this has blocked the research for a lot of time, and it's kind of amazing now to see this system that follow a totally different computational path. And by the way, our brain is everything except Occam razor kind of system, right? It has an enormous number of weights and so on, of synapses and so on. But this was a big obstacle. Okay, so now we are in the situation, enormous systems. So let's go through together the experience with a little bit more of maybe detail with respect to what you might have personally experienced. Let's go back in time a couple of years, and let's see what has really surprised us. And also I would like to show you these few examples, because it gives you an idea of how quickly the field is changing. It's really quite incredible. So I'm going to describe what happens December 2022 compared to April 2023. So 4 months. What happens in 4 months, okay? With language models. So we started with GPT-3, the first version of GPT. We were surprised and we were making fun of it because it was writing fantastic answers that made no sense, you know. We were a bit, and so let's consider one example. So here's the prompt. I don't know if you can read it. The prompt says, here we have a book, 9 eggs, a laptop, a bottle, and a nail. Please tell me how to stack them onto each other in a stable manner. That was the question. And so we asked this to ChatGPT, Christmas 2022, and we had a lot of fun by observing that the answer was the following one. Take a bottle, take the nail, put the 9 eggs, put the laptop, and then put the book. Oh, what a stupid system this is, right? Now, let's wait a few months and go to GPT-4. Same examples, now an increase in size of 1 order of magnitude, same prompt. Here you can see the written answer, but I draw the picture so that it's simpler for you to understand what is written. It says, start with the book, place the eggs regularly so that the forces are distributed, put the laptop, put the bottle, and put the nail upside down so it's in equilibrium. What do you say? This has learned something about the physical model underlying the prompt, and it's kind of impressive. You know, Geoffrey Hinton, who got the Nobel Prize for his model and was working on this, never recovered from this experience. He actually quit Google at a certain point, and now he's telling everybody that AI is a danger, because this was too surprising for him. Okay? Another example, again, I'm comparing Christmas 2022 with April 2023. So this is a conversation between Mark and Judy. They are talking about the behavior of their son. Okay, and Mark says, I don't like how you treated Jack last night. And Judy, did you see what he was doing? Hit his brother on the head. Mark, that doesn't justify you yelling at him. And Judy, what do you want me to do? Let him beat his brother up and say nothing? Mark, no, I don't. Then why are you defending him? Now, given this conversation, you ask ChatGPT, what does Mark's intent seem to be? Okay? This was ChatGPT 2022 said, based on the conversation, Mark's intent seems to be to defend Jack's behavior and to express his disapproval on Judy's treatment of Jack. This is wrong. Totally wrong. Very well written in English, but totally wrong. Again, we can make a lot of fun of this, but if you wait 4 months, then you get this answer. Mark's intent seems to be to express his displeasure with Judy's way of handling the situation, etc. So it got the answer right. Okay? So this is very important because it tells you that it's capable of understanding human language pretty well, and this is at the root of all the applications we see today. This was again some common tests. The penultimate column is the SAT test for entering various types of university entrance test, and you see that GPT, actually this was already 3.5, so it was even, anyhow, the score of ChatGPT, the first version was 1,210, the maximum is 1,600, okay? But then, and this is not enough to enter most of the university, but then the first version of GPT-4, so April, the score was above 1,400, which is enough to enter in most universities. And nowadays, you cannot do, it's just saturating, okay? This is another interesting example. Again, comparing GPT-3 and GPT-4, the prompt is the following. Produce a JavaScript code that creates a random graphical image that looks like a painting of Kandinsky. Now, I put a painting of Kandinsky in the middle just to give you, to remind you of Kandinsky, but at that time, there were no diffusion models, so it was not possible for the AI to create directly an image. So the only thing that the AI could do is to create a code that then could be run on another, say, computer and produce an image. So it could not generate directly the image. So the prompt was write a JavaScript that produces certain images using simple graphical primitives like circles, straight line, triangles, and so on. Now, on the left, you see the answer at Christmas, GPT-3. Has nothing to do with Kandinsky. On the right, you have the answer of GPT-4. Not bad, eh? I mean, just using triangles, circles, and straight lines. Again, this in the range of a few months. By the way, how is it possible that so where did I get the data? It's kind of a socially interesting fact. For 4 months, the only people who had access to GPT-4 were researchers of Microsoft. And so for 4 months, they could make experiments with these tools, and then they published this paper, which is called Sparks of Intelligence, something like this. So again, here we have a problem. You know, for 4 months, this incredible tool was in the hand of a small group of researchers that could that had total access to it, and nobody else had this kind of possibility. Okay. Okay. So now let me just continue, assuming that you want to know the basics of AI. First of all, about terminology. Now, when we talk about AI today, we mean machine learning. Okay, so in the 50s, 60s, when we were talking about AI, or in the movies, AI meant human-like intelligence. Okay, but then in the last 20 years, somehow the term was downgraded just to mean machine learning. So machine that learn from data to do interesting stuff. Okay. So today, when we want to talk about artificial intelligence, we have to use the term artificial general intelligence to talk about, say, human-like intelligence. Whereas when we say, and when we read about artificial intelligence, what we actually mean is just machine learning. Okay? Just a matter of terminology. So if I say artificial intelligence, I mean machine learning. If I say artificial general intelligence, I mean kind of thoughtful machines that can do very human-like things, which do not exist. Now, sorry now for being a little bit more concrete, but so what has allowed what has led to the AI revolution are learning methods. Okay. Now there are 4 learning methods. One is so-called unsupervised learning, which is data clustering, things that we have been doing for hundreds of years. Okay? And then there are 3 types of learning that are more modern, which are called supervised learning, reinforcement learning, and self-supervised learning. Now, these approaches have led to modern, say, AI. So I'll kind of describe them very briefly so that you have an idea. Because at the end, if you, I mean, knowing something about AI today, for me, it means, and I think it's very useful for everybody, I mean also people working in humanities, is to have an idea of where the power of this system comes from and the limitations. So we have to go through these kind of arguments. So in traditional AI, so in order to introduce these methods, let me mention what we have been trying to do for many, many years in artificial intelligence, and that has produced a lot of failures. So in traditional AI, that one that never succeeded, what we wanted to do, what we tried to do, is to make prediction based on some a priori concept of what the answer should have looked like. So for instance, suppose that you have to write a code that tells you whether in a certain image there is a chair or not a chair. Very simple task. What you would have been doing in the 90s, say, it would have been the following. Write a code in your favorite computer language of the type, of the following type. You know, if the object has 4 legs, a flat surface to sit on, and a backrest, then it is a chair. Okay? And this works perfectly for the first chair over there. But already for the second chair, it doesn't work because it doesn't have 4 legs. So what you have to do is actually to, to modify the first condition and add another condition saying if it has 4 legs or 5 wheels and a flat surface and a backrest, it is a chair. So you have to go back and modify the code. But if you show the third example, taken from Milan, again, you have to go back and modify because it doesn't have 4 legs, it doesn't have 5 wheels, it has some curly kind of legs, and so you have to go back and modify the code. And then, you know, if you are presented with a chair like this, then you have to go back and write what? It's not clear. So all this approach comes from the notion that somehow there exists some basic features of the object, and our only task is to recognize the presence of these features in the image. And this is totally wrong, and it has never worked. Okay? So you see, in this example, I don't know if you can see it, but these are many examples of chairs which everybody can recognize if you look carefully. Also, a cat can recognize it. And still, there's no way of encoding a priori what they are. And so the idea is that we have to abandon completely the approach in which we just check for the presence of certain features and go towards a different approach, which is learning from examples. Okay? And we will see what this means in a minute. So when we talk about neural networks, AI system, you can mentally imagine this system as an object like this, in which we have an input layer, say on the left, and then some nonlinear unit that processes the information. So the information enters on the left and goes out on the right. Okay? And at each nodes behave, vaguely speaking, like a biological neuron in the sense that it is a nonlinear unit. Essentially, let's take the blue node over there. And in that blue node, what you can see is that what happens is that it takes the sum of all incoming signals, and if this sum is above a certain threshold, then it emits a signal to the subsequent layer. So in this way, there is a very complicated nonlinear transformation from the input to the output. And please keep in mind that this is just a little sketch. A real network has 10 to the 12 connections. So something that you cannot imagine, okay? And you can imagine that these connections are like tubes, right? In which some, say, water can flow. And so each tube can have a different diameter, right? So the bigger is the diameter, the more water can flow, right? So the interaction between, say, neurons depends on the diameter of the tube. So similarly, in these networks, each connection has a weight, a number, that determines how much a certain node influences another node. So essentially, learning means that we have to find all these 10 to the 12 parameters such that this network does what we want. And this is the scope of learning. And there are various ways of doing this. It can be through supervised learning, reinforcement learning, or self-supervised learning that we will see in a minute. But this is the objective. And it's kind of mentally useful to imagine that what the first layer do in this network is to learn how to decompose the signal coming from the input in such a way that the last layer can use this decomposition to actually reach an answer. So somehow, the first part of these layers are doing what we were trying to do by identifying the characteristic features of the object we have to recognize. The difference being that the network will learn how to decompose the image. We will see this in a minute, but you can ask. Now, let's keep the connection with biology. So how does learning take place in this system? Well, it takes place just by showing a lot of examples. In the case of supervised learning, in the case of supervised learning, we have the input and we have a label for the output. So for instance, we have an image, and then we know, because some human being has observed the image, that the image contains a chair. So we can also add the label, yes, there is a chair, or other objects, okay? So we know both the input and the desired output. Then what we do is that we feed on the left the image. Each node gets 1 pixel of the picture, say. And then what we do is observe the output. If the unit that corresponds to the, say, the labeled chair lights up, becomes active, then it means that the network has done what we actually want. But if it doesn't, then a learning process sets in. All the weights are modified slightly in order to favor the correct answer in output. Okay? And this process is repeated millions of times on millions of examples until the network is capable of answering correctly to all the examples you provide to the network, which can be millions. Okay, so a very famous data set is the MNIST data set, which is, these are handwritten digits that the machine has to recognize. And this was one of the first successful examples. I mean, in the US, since many years, if you want to cash a check, you just give it to a machine, and the machine reads the amount. There's no human intervention, okay, because it's based on this kind of codes that can recognize handwritten digits. Okay, this is a little movie of how learning takes place. So you see, you feed in an image on the left, say a 4, and you look at what the answer is, and if there is a mistake, you backpropagate a signal that modifies all the weights. Okay, and so you repeat this on millions of images and so on and so forth. It looks like with no hope, but it actually has a big, is very successful. I don't know if you want to see a neural network at work. You want to see it at work? So let me try to. So this is something you can actually play with. It's called neural playground. So the idea is the following. So you have this. Let's say, let me start with a simple data set. Okay, let's say that these are the data. The points that you see, the yellow and the blue ones, are data points, and you want to learn to classify yellow versus blue, okay? Such that when you show new data, this bolded one, you're able to make good predictions. So essentially, you would like to be able to kind of identify a decision boundary that separates the regions where blue points are and yellow points are, okay? So let's see what happens. Okay, let's start with a very simple neural network. You have 2 input nodes, which are the 2 coordinates of the points, and then you have 4 neurons, say, in the layer, and then directly an output neuron. So a very, very simple network. We provide this example, and then we have a learning algorithm that starts, and this is the decision boundary that the machine finds. Okay, and you see that if you show some new data, it works perfectly, right? And so, by the way, by looking at this connection, you see that this is a weight that has a value minus 0.72. This is a weight of 1. This is a weight of 0.36. Where do this number come from? From the training procedure, okay? This back and forth procedure that I was talking about before. But this is easy. So let's take this other example. This is a bit more complicated. And let's see what happens. And so we start again. These are the data points. And you see, OK, it works again. Even so, this simple network is capable of separating the space of possible input in regions such that it's going to make good predictions. Now, let's make things a little bit more complicated. OK? Let's try and see what happens. And again, you know, this kind of simple network is still capable of doing this. Okay? But now let's go to something tough. Okay? You want to be able to train a network that understands on which branch of your spiral you are. Okay? And if you try to do this, there's no way of making this network work. So I'm not going to wait a lot. It doesn't work. So we can modify, and we can add a couple of layers, a lot of neurons, you know, just kitsching here, and maybe even, you know, give more information. Then I change the the nonlinearity of the neurons, and then I regularize, I do a lot of things that I'm not going to describe, and then we can see what happens. It's not an easy process, but maybe it works, maybe not. Okay, you see it works. It was able to generate a partition of the space with this non-trivial image. Okay? Now, why did I show you this example? Because just because where is it? Sorry. Okay. In 2 dimensions, one can easily see what's going on, but in reality, the inputs are very high dimensional. So let's say if you apply this machinery to, let's say, medical data, and you plug in gene expression data, you have 25,000 inputs. Or if you apply this to, I don't know, astrophysics kind of data, it's also very complicated, and so on and so forth. So something that defeats our imagination. Okay? Now, what I was trying to tell you before is that along the learning process, what happens is that the layers, the neurons in the first layer, learn to become active when certain features are present in the input. They learn this. You're not defining this a priori. So for instance, if you train a neural network to distinguish digits and so on, you discover that the neurons in the first layer are reactive to different type of input patterns, kind of filters. It's like, in algebra when you have a basis, to express your vector. Here you have filters, and so by looking at this filter, you understand which is the optimal way of processing the input in such a way that then it's possible to do something with this processed information. This was a big revolution of modern AI. So put order in a very complicated data set. And so this was one of the key differences between the good old-fashioned AI that didn't work, which was this idea of pretending to be able to recognize things just by recognizing the presence of certain features in the inputs, with respect to modern AI, in which the machine learn how to optimally process the input in such a way that they can do things later on. Okay? So this is what marked the revolution in terms of time scale. So 2012. In 2012, Geoffrey Hinton from Canada trained a network that now is famous. It's called AlexNet. Probably you will see it in some movie at a certain point. But AlexNet, this was a relatively small neural network that he trained to participate to a competition which is called ImageNet. And the competition goes as follows. You have images. Each image can contains many objects. And the task is to tell whether the image contains an object belonging to a list of 1,000 possible different objects. Okay? So you have a list. You have to, given an image, you have to say which objects are present in the image in a list of 1,000 alternatives. Now, human performance are around 5% of error in this kind of task. And in 2012, the best computer algorithm for this, Pietro Perona was working on this kind of stuff, had a performance of 26% of error. Then Geoffrey Hinton and his group, with this first neural network, were able to bring down the error rate by 10%, which is a huge amount. And so in that year, it was a very critical situation. It was in 2012, it was impossible to publish a paper saying that you're doing pattern recognition using neural network. The scientific community would have not accepted this kind of approach. But then in 2013, what happened is that you would have not been able to publish a paper in the pattern recognition community without saying that you were using a neural network. So there was a real shift, a lot of fights and so on, and everything changed completely. But since then, now these networks are actually able to recognize objects in scenes with very high accuracy, much better than human beings. Okay? So this is how it works. You have an image. The first there is you divide in boxes your image, and then inside each box segmentation is called, sorry. Inside this box, you have an object, and then the program is telling with which probability there is a certain object in the box. Okay, so and this is why we are talking about self-driving cars, just talking about it, because they see very well. They see very well. No problem in recognizing structures in the scenes. They're very good at it. Taking decision is another issue. And this is what happened, you know, in 2012, things set in, and then in 2013, the big tech companies started to invest in this field. Some of you are students, and so you might want to know that Zuckerberg went to the conference of machine learning offering PhD position for $1 million per year of salary. So, and this has changed completely the scenario in the sense that it was a big hit for universities, and now we are in a very complicated situation in which a lot of good people are working for these private companies. And so, but we will have time to talk about this, okay? Maybe I skip this because it's not clear how much time I have, but there's been a continuous of progress. But I would say that there was this first revolution in 2012, and then there was a second revolution, say 4 years ago, with generative AI. Already the first AI is actually could be very useful in the sense that, for instance, for breast cancer screening, it could be used just by looking at, you know, mammographies and highlighting situation of danger, and is actually used in Massachusetts, but it's not used here. Why? Just because it's too complicated to organize, not because there's a technical limitation. Okay, so but this could be used. It's already used, and it has already been validated because it has been in use for 2 years, and since then there's been an evaluation ex post, and it works. So why do we talk about AI today and not, say, 10 years ago? What has happened very quickly? First thing that happened is that in 2005, as you probably know, some of you play with a computer, and in order to play with a computer game, you need GPUs. You need a particular hardware that makes the graphics particularly pleasant. And so the electronic industries have produced these graphical processors in the context of gaming. Now, what scientists discovered around those 2005 to 2006 is that they could use these kind of processors that were very cheap, let's say less than €1,000, to actually do matrix multiplication very fast, which is the essential operation that you do when you do the training of neural networks. So since then, what happens is that in many labs around the world, scientists all of a sudden could have on their desk a computer which was faster than the fastest computer that existed in the year 2000. So all of a sudden, for very little money. And so this is the reason why people started to make experiments, and this is the reason why theory is behind practice, because people were able to make a lot of experiments. So this is the first thing. All of a sudden, cheap tools became available. And now what we talk about are these cloud centers in which, like this one, in which you have hundreds of thousands of GPUs that work in parallel, okay? Just to give you an idea, Cineca, we have a computer center in Cineca. What was the name? I think Leonardo. No, Leonardo. Oh, okay. It doesn't matter. It has, I've been there. You have these racks of GPUs, and they have 14,000 GPUs. Now, if you take any lab of Meta, it has more than an order of magnitude GPUs in the lab, which means that we as a country have a national computational facility which is a fraction of any lab of any tech giant. This is a problem. And then, of course, data. Data became available around the year 2000, so these two things actually helped the growth of AI. And so now we are in this incredible situation in which we can take an image have a neural network that is able to recognize what is in the image. Then we have a language model that takes these answers and creates a description of the image. Now, it looks simple. I mean, for the young students, this is totally obvious. I mean, not because they understand, but just because they're used to it. But if you think about it, I mean, 5 years ago, this was just considered to be science fiction. Now, there is another form of learning, which is called, there's an Italian thing, reinforcement learning, which is the second type of learning that is used in robotics, for instance. So the idea is that you have an agent in some world, and the behavior of the agent is controlled by a neural network that, given an input, tells the agent how to behave. And the modification of the weights is given by the reward that the agent gets from the external world. Instead of having a supervised answer, having an answer, and so being able to check whether the answer is correct or not, here the error signal comes from the reward of the environment. I don't know if this is clear, but this is the second type of learning. So you have this robot, you put it in the world, and it starts to move. At the beginning, it's behaving very badly, but then it gets some reward, and it learns to. So here it is, the first example. Again, 2012, look what happens. This is an Atari game. I don't know, you must be very old to know what an Atari game is. It's just, so the computer just sees the pixel of the screen, and the reward signal is just the number that appears on the top. And the game goes as follows. You have to train your paddle to bounce back the ball and to destroy as much as possible the wall above. And you see, the reward is the number 003 up there, 004, and so on. So at the beginning, the network controls the position of the paddle. Okay? And at the beginning, after some time, it starts to learn how to make the ball bounce back. And then after a lot of gaming, say, you see, it learns. It's not very certain in its movement. It's not like Jasmine Paolini, but then look what happens after 600 epochs. Okay, after a long time. You see, you have this machine that has learned how to play the game, but then something happens strange that the ball goes back, and so the reward increases a lot. So, and then it learns immediately that it's better to send the ball behind the wall because this gives a larger reward. So it has learned a strategy. That's the thing. So by the way, this was published in Nature. It was not, so it's a very kind of a serious thing, but it has learned a strategy. And so a friend of mine used this approach to actually train an automatic pilot for a glider in California, and he was able actually to set up a pilot, and then, here, sorry, I have the movie, but somehow I didn't put it in the presentation. But so this glider was able to exploit the hot air coming from the ground and just keep on flying for as long as possible. And this kept on flying for the whole day without problem. So he succeeded very, very nicely. And this is why, you see, this idea of playing games and adapting based on the world can be used to play games. For instance, there's this very famous thing that happened in 2016 in which this network became able to play Go, not only chess. Chess is trivial. Go is a very complicated game because you have a 19 by 19, so an enormous space to move, and the number of alternatives at each move is very big, so the tree of alternative grows exponentially very, very fast. So there's no way of doing an exhaustive search here. And what happens is that by playing a lot of games, this network learned strategies, not through an exhaustive search, but by learning strategies. Okay, so they succeeded, and they became able to produce new moves in the game, and so much better than human. Here's another example. Okay, this is a virtual world in which the blue guys are governed by a neural network, the red guys also governed by a neural network, and the red guys want to hit with their ray the blue guys. And the blue guys get a reward if they are not hit. Okay, so there's this game one against the others. And you see the red guys are actually very happy, but at a certain point, the blue guys learn to block the door. Okay? And so they win. And they learn to block multiple doors. But then you put a ramp in the scene. It's an artificial scene. And so you can do whatever you want. You add tools. And you see, at the beginning, the blue guys just block the doors. But then the red guys learn that they should climb the ramp and go inside to hit the blue guys. And so the blue guys learn that they first have to remove the ramp and then close the door, not the other way around, and so on and so forth. So you see, but what is the problem with what I've described to you? It's wonderful. This is a very powerful learning procedure, but there is a problem. If you want to learn how to drive using this method, you have to do millions of accidents before you learn. So this is not practical. It doesn't work in the real world. So our brain cannot work like this. Even though whenever you can actually simulate reality, then it becomes extremely useful. So for control situation in which you can make an efficient simulation, then this becomes super useful. Okay, I'll skip this. This is how they train cars, self-driving cars to drive. So self-driving cars are trained on simulated environments, also in real environment, but mostly on simulated environment, but they're still not very good at driving. I mean, I don't know who of you has taken Waymo in San Francisco. There are 300 taxis there, but their behavior has been tested. It's statistically worse than the average driver, which means it's like, you know, going in a car with a very stupid driver. That's the situation. And so it's not going, and it's kind of saturating. Right? We have been talking about this since quite some years. I think it's more than 8 or 9 years that we are talking about these self-driving cars and still not there. So this idea of having neural networks that interact with an environment has led to what is now called generative AI. So let me just tell you, this is also very, very important. Let me tell you how the first model of generative AI used to work, because I think it's kind of pedagogical and useful. So that is the following. We already know that we can train a neural network to recognize object in an image, which means that we can train a neural network. For instance, we could train a neural network to discriminate between real images and images that have been modified by, say, Photoshop. Fake versus true. We know already that neural networks are better than humans in doing this, just like they are better than humans in recognizing objects inside an image. So what we can play the following game. We first train a neural network to discriminate between true and fake images. And then we train another network to generate images that fool the discriminator. Okay, so we can play this game. So train a neural network that is capable of fooling the other neural network that is better than human in recognizing fake versus reality. Okay? And it works very well. Okay, this is an example. You take this generator network, you provide this input. The network has never seen this image, so it's not recognizing something. It's completing the image in such a way to fool the discriminator. Okay, it's a totally different approach, and this is the output. Okay, or you give this image, and this is the output, and this person does not exist. Or say, you take this image, you delete the information that there is a man behind the bar, and then you ask to complete the image, and it provides an image like this. Or you can give a low-resolution image and get back a high-resolution image. Okay, all these kind of things. This was in 2014, 15, so it's old stuff, almost forgotten. Okay, and now these things have been substituted by another type of generative AI, which are called, in the case of images, diffusion models, which work on different principles. Maybe I'll get back to this tomorrow because it's a bit, it takes a little while, but let me just mention to you that essentially what Okay, how does this system work? This works as follows. You take an image and then you add noise. And you train an actor to learn how to remove the noise that you have added. Okay? Then once you have done this, you invert the arrow of time. And you start with noise. And by inverting the arrow of time, the network creates an image. In principle, if the image has been trained on a set of images and have learned to remove noise from this set of images, when you reverse the process, you should reproduce the same images. So it's not very useful. But if you introduce some, say, imperfection in this process, what the network is then will be able to do when you stimulate with some noise is to reproduce images that are statistically in the same class of the images on which they've been trained, but that are different. Okay? It was a very, very fast description. It's based on diffusion equations, but this is just for those of you who are interested. And it can be used, say, to improve images, to create totally new images. You can even go, you see, by using language models, you can actually start with the text and ask the system this text is going to produce some proper noise, and then this produces an image. And this is an example of that. Or you can even use it for movies. Okay? Again, this is an evolution of diffusion models. For instance, you give a prompt. Archaeologists discover a generic plastic chair in the desert, excavating and dusting it with great care. Given this prompt, the system produces the following movie. At the beginning, it looks very reasonable, but then it starts to hallucinate because the chair starts to fly. It looks very normal at the beginning, but that's the way it goes. And there's one thing that I always like to point out. Oh, sorry. The fact that you can recognize, among other things, that the system is not working very properly because, let me see if I can stop it in the right moment. This guy, here you cannot see it, but has 6 fingers, which is a typical mistake that AI does in this kind of things. So nowadays we are able to, to use this system for generating images, and I just put this together this morning. I don't know if this is a prompt that I've given to AI, and I asked the joy to be a coat hanger. La gioia di essere un attaccapanni. Now, Anna knows what I'm talking about. And here you see 2 examples. One is generated by AI, another is generated without any artificial intelligence, just human intelligence and very elementary tools. And you see the difference between the two. I mean, you can imagine that the first one was generated by diffusion models, so it puts together in a very, not really fun, I would say, in a very dummy way, all the information that you are given. You see there are some codes, there's a hunger, and then there's the joy. It puts things together. But that's it's not a lot of fun. In the other case, that's a picture of Tullio Regge, who was playing with the idea of this coat hanger that are dancing in a strange world, which is kind of creative. And so this is the situation for, I mean, this kind of system can be used for arts, but in a very specific way. Now, let me just conclude this first part by, I've told you, well, you can train the system with supervised learning, in which you know the input, you know the output. You can train it with reinforcement learning, in which you train your system based on a reward that you receive from the environment. And then, but the problem is that most of the data are not of this type. You cannot supervise all the data. Every day we produce an enormous amount of data in the world of various sorts, and there's no way we can label them. So we need a different approach. And this is what is called self-supervised learning. I've already mentioned to you this in the beginning. So let me go through this again, because I think it's very important. So let me take a random sentence in Italian. And so what we do is the following, is that we take the sentence, we just mask a word, and train the network to learn what we have masked, to guess what we have masked. And we repeat this in all possible combinations, okay? And this is the way modern language models are trained. They are actually trained in a specific way in which they are trained to predict the next word. So essentially you delete the last word of the sentence and you train the network to predict what is missing, so that it's capable of continuing completing a sentence. Okay, and how language model work is that once they have done this, you give a prompt, they guess the next word, and then what they do is that they take this word and attach it to the input. And then they predict the second word, and then they bring it back in the input and so on with this loop. It's called autoregression, okay? And this is the way the language model work efficiently. Maybe we can go back to this in another moment. Okay, let me just then tell you that nowadays what's happening is that these systems are trained not only with text but also with images together. It's called multimodal learning. And this is the state of the art for, say, passive kind of AI, very powerful. It's like, a Wikipedia in a very dynamic environment. We can, ask any question, get answers. But keep in mind that the answer we get depends exclusively on the input we give. So this has led to the field of research which is called prompt engineering. So given the system, how do we prompt the system in order to extract the information we really want? So there are many things you can do to improve the output, but everything is driven by our input. There's no objective in these systems. So you cannot ask ChatGPT never ask ChatGPT to make a plan. It will answer, because whatever you ask is going to answer something, but it's not built to solve a problem. It's built to answer prompts, which is a different, so you have always to guide it, okay? So maybe tomorrow we can see how this thing can be used to produce the first forms of artificial general intelligence. So there are ways now to do a smart prompt engineering that leads to reasoning capabilities. I believe, but many others believe, that this is going to saturate and is not going to be the way where we reach AGI, but it's worth talking about it. So tomorrow we talk about how to move towards AGI and also talk about which are the alternative models. Okay, and then we'll talk about application in science, and then what has physics to bring, what can physics bring to the table of all this. Okay. I stop here today. Okay.